Hello and welcome to another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson 2 on adding and subtracting polynomials. So we introduced polynomials in our last lesson, all right? Introduced a lot of terminology associated with them, and that's where we're going to begin today. We're going to review both the idea of polynomials and the terminology associated with them, and then we'll take a look at how you can add and subtract polynomials. So let's get into it. Now, polynomials as generalized whole numbers. Polynomials are very similar to whole numbers that are written in terms of powers of 10, except polynomials are written in terms of powers of x or some other variable. So let's kind of review that similarity in exercise number 1. Given the number 5,738, do the following. Letter A, write the number as a sum of multiples of powers of 10. All right, well, we did this in the last lesson. What I'd like you to do is try this again, right? Remember, you start off by writing it as 5,000 plus 700 plus 30 plus 8, and then you go from there. Pause the video now and see if you can do letter A. All right, so let's do it, right? This number is the same as 5,000 plus 700 plus 30 plus 8. 5,000 is, of course, literally 5 thousands. 700 is 7 100s, 30 is 3 tens, and 8 is just 8. Now, 1,000 is the same as 10 to the third. 100 is the same as 10 to the second. 10 is the same as 10 to the first, but I'm just going to leave it as 10. And then we have plus 8. All right. Now, this is literally how we are able to write whole numbers as big as we want. If we had 3,725,322,165, we could write all of this out, and of course we're only using the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? But we're able to write very large numbers because we're just kind of keeping track of these consecutive powers of 10 and how many of them we have. Now, we can change this into a polynomial in letter B. If x equals 10, write the number in terms of x. Well, this is simple, because as soon as I see a 10, I'm going to replace that with the letter x. So this entire number then could be represented as 5x cubed plus 7x squared plus 3x plus 8, right? That number and this polynomial expression are identical as long as the value of x is equal to 10. All right, now let's review some terminology that we saw in the last lesson. Recall that a polynomial is the sum of algebraic terms where all of the powers are whole numbers. That's absolutely key. We can't have any powers that are fractional, although you haven't even seen those yet. But we also can't have any powers that are negative, all right? So let's take a look at exercise number 2 so that we can review some of the important stuff we saw in the last lesson. Let's take a look. Consider the polynomial 7x minus 5x to the third minus 8 plus 3x squared. Letter A, write the polynomial in standard form. All right, see if you can remember how to write a polynomial in standard form. Pause the video now and take a few seconds, really, to do this. All right, well, remember, in standard form, a polynomial is written such that its powers decrease from the highest down to the lowest. Now remember, we got to bring our sign with us. So the highest powered term is negative 5x to the third. Then we've got plus 3x squared. Then we've got plus 7x. And then we've got minus 8. Right? So we've got x to the third, x to the second, x to the first, and then no x's at all. Letter B. What is the leading coefficient of the polynomial? All right, well, see if you can remember what that term means and see if you can write down what the leading coefficient of this polynomial is. All right, well, a coefficient is simply a number that multiplies an algebraic variable, right? The leading coefficient is going to be the number that multiplies the highest powered term. So in this case, the highest powered term is x to the third, and therefore the leading coefficient is -5, right? You can also think about it as really being the first number you see once you've written the polynomial in standard form, right? That -5 is the first number. That's why it's called the leading coefficient. Letter C asks us for the degree of the polynomial. Pause the video now and see if you can write down what the degree of the polynomial is. All right, well, the degree of the polynomial is probably the simplest thing about polynomials. It's the highest exponent, the largest exponent, right? In this case, right, the degree is equal to 3. Sometimes we would call it a third degree polynomial. The degree of a polynomial controls a lot of its behavior, how fast it grows, how many turning points it has, how many zeros it has, all sorts of things. Now finally, a piece of terminology we didn't see in the last lesson. Let's take a look at letter D. What is the constant term of the polynomial? All right, this one's kind of cool. The constant term of a polynomial is simply the term that doesn't have any variables in it, right? Like literally, variable and constant are opposites of each other. A constant is something that is constant. It doesn't change. And a variable is something that varies or does change. The only term that is constant here is -8. And it is -8. It's not +8. Okay? Now, in standard form, the constant term will literally be the last thing written if it's even there, right? If everything we had here involved an x, then the constant term would actually be 0, okay? Every polynomial technically has a constant term, even if it's not there, and if it's not there, the constant term is 0. All right, now let's get into the heart of what we're doing today, adding polynomials. Because polynomials are similar to whole numbers, they add, subtract, and multiply in similar ways as well. In this lesson, we're only going to be dealing with adding and subtracting them. So let's see how we can make that connection by looking first at adding a couple whole numbers. Exercise number 3. Consider the numbers 523 and 271. Write each as the sum of multiples of powers of 10 as previously done. Okay, so I just want to write these things out kind of like I did before. Let's do this together, right? So we've got, 523 is equal to 500 plus 20 plus 3, and I'm going to write it right away as 5 times 10 squared plus 2 times 10 plus 3, right? And 271 is equal to 200 plus 70 plus 1, which is 2 times 10 squared plus 7 times 10 plus 1. All right, simple enough, right? Now, I want you to really keep in mind what each one of these says. What each one of these says is 523, right? When I write it like this, I can think of this as, well, I've got 5 100s, I've got 2 10s, and I've got a 3. In this case, I've got 2 100s, 7 10s, and just the number 1. So in letter B, it asks us to add these numbers by adding each individual power of 10, right? So what I'm saying is that I can literally look at this and I can go, well, I've got 5 10 squareds and 2 10 squareds, so I must, when I add them together, get 7 of them, right? Then I have 2 10 to the firsts and 7 10 to the firsts, so when I add them together, I must have 9 10 to the firsts. And finally, I have my constant terms, 3 plus 1, and that just gives me 4, right? So I'm just keeping track of how many hundreds do I have, how many tens do I have, and how many single digits do I have. So since I have 5 hundreds and 2 hundreds, when I add them together, I have 7 hundreds. I have 2 tens and 7 tens. When I add them together, I have 9 tens. And finally, 3 and 1 gives me 4. And of course, then I can say, well, but that's actually the number 794. Now, side note, if you're sitting back right now saying to yourself, I would never ever add these two numbers by doing this, and then converting it back to here, I would just do 3 plus 1, 2 plus 7, 5 plus 2. I get that. But the reason you can do that is because of this. We are literally just keeping track of how many tens, hundreds, etc. Now, the one thing this doesn't take into account is what would happen if we, let's say, added these two things together and somehow we got a number bigger than 10 and we'd have to carry some digits and things like that. We're not going to worry about that right now. But let's now take that and go to letter C. Use this idea to add 5x squared plus 2x plus 3 plus 2x squared plus 7x plus 1. You see, it's the same thing, right? There is virtually nothing different between adding these two things together and adding these two things together. The only difference is here it's an x and here it's a 10. But down here I can say, well, okay, I need to keep track of how many x squareds I have. Well, I have 5 of them and 2 of them, so I have 7 of them. Then I need to keep track of how many x to the firsts I have. Well, I have 2 of them and 7 of them, so now I have 9 of them. And then I keep track of how many single digits I have, 3 and 1, and that gives me 4. Now notice I don't do anything weird like say x squared plus x squared is x to the 4th. I didn't do that up here. I didn't suddenly say change those 10 to the seconds into 10 to the 4ths, right? I'm literally just keeping track of how many of each type of term I have. I have 5x squared, 2x squared, which means I have 7x squared. I have 2x, I have 7x, add them together, I have 9x, and then here it's just normal addition. 3 plus 1 is 4, right? It's simple. So simple that I think you can now do letter D on your own. Let's take a look. Find the sum of the polynomials negative 4x squared plus 9x minus 3 and 7x squared minus 5x plus 4. All right, I'm going to actually take a look at this 2 different ways, but first I'd like you to do it on your own, or at least take a try at doing it on your own. Pause the video now. All right, well, one way to do this problem is to kind of stack the 2 polynomials vertically the way we did it right here. In other words, I can literally do like, let me write out the first one, negative 4x squared plus 9x minus 3, and then 7x squared minus 5x plus 4. Right, when I add these together, I'm going to have negative 4x squared, positive 7x squared. When I add them together, I'll have positive 3x squared. Positive 9x plus negative 5x is positive 4x. And then negative 3 plus positive 4 is positive 1. Right, 3x squared plus 4x plus 1. That's one way to do it, right? Another way to do it is to literally, again, go back to this idea, right, that what I'm doing is I'm simply adding up how many of each type of term I have. So I could literally say, well, for my x squareds, I have 7 minus 4 x squared. Then for my x to the firsts, I have negative 5 and 9 times x. And then for my constant term, I have negative 3 plus 4. Right? So literally, I'm kind of more formalizing it. Like I've got the 7 and the negative 4, and they're both attached to the x squared. So I have to combine those. Then I've got this 5, right? This negative 5 and this positive 9. I'm going to add those two together, and that's how many x's I have. And then my normal numbers, my constant terms, right? I've got that negative 3 and that positive 4. And at that point, I can say, well, 7 minus 4 is 3. Whoops. 3x squared. Then I can say negative 5 plus 9 is 4x, and negative 3 plus 4 is 1. Whichever way is easier. All right. I will probably do it more and more like this simply because it saves me some room, but you can also stack them vertically, which then mimics the natural way you would add 2 3-digit numbers or 4-digit numbers or whatever. Let's do some more of these. All right. When we add 2 polynomials, as I've mentioned again and again in that last exercise, we're simply keeping track of how many of each power term we have in the polynomial. We're combining like terms, right? Remember, like terms back from Unit 1 are terms that have the same variables, raised to the same powers. And those you can combine by simply combining their coefficients. Let's take a look at how to do that in exercise number 4. Write each of the following sums in standard form by combining like terms, variables with like powers. Arrange the sums vertically in standard form if needed to help combine coefficients of like powers. Okay, so here we go. Let's do one where we don't, where we don't arrange them vertically. I've got 9x squared plus 7x plus 2 plus 8x squared plus 3x plus 5. I want to add these together. All right, so I could do that by saying, well, I've got 9 plus 8. Those are my x squareds. Then I've got 7 plus 3. Those are my x to the firsts. And then I've got 2 plus 5. And those are my constants, right? Therefore, how many x squareds do I have? Well, I have 17x squareds, 10x to the firsts, and plus 7. Very simple, right? In fact, I have no problem when students basically just look and go, well, I have 9x squared plus 8x squared, that's 17x squared. I've got 7x plus 3x, and that's 10x. I've got 2 plus 5, and that's 7. 17x plus 10x plus 7. All right, no problem. Now, it can obviously get dicier when you start to add things that have negative numbers in them. So let's take a look at letter B, where we've got negative 3x squared plus 6x minus 5 plus 2x squared plus 4x minus 7. All right, so let's take a look at this. Now again, it may be advantageous to think about like the negative 5 here as plus negative 5, and the negative 7 here as being plus negative 7, right? But again, thinking about this the way that we just did, I could literally say, well, in terms of x squared, I've got that negative 3 and that positive 2. In terms of x to the first, I've got that 6 and that 4. And in terms of my constants, which I need to sneak in here, I've got that negative 5 and that negative 7. Right, so now I have negative 3 plus 2, which is negative 1x squared. 6 plus 4 is 10, so that'll be 10x squared. Negative 5 plus negative 7 is negative 12. Now I'm going to circle this, and then we're going to rewrite it in a little bit of a different way. All right. Whoops, that shouldn't be an x squared. That should just be an x to the first. My apologies. So that's negative 1x squared plus 10x plus negative 12. Most people will not leave it that way for a couple reasons. One, they tend not to leave a negative 1 there. They'll write it as just negative x squared. And then we tend to not leave plus minus 12, just rewriting it as minus 12. Right? So this is the far more common way that you'll see it. There's nothing technically wrong about that. All right? This is as good of a standard form as this one is, but this would be the way that you might see it if it was a multiple choice question. All right. Now, in both A and B, both polynomials were written in standard form, so it was pretty easy to kind of see how to combine them using addition. If we look at letter C here, right, we've got 6x minus 2x squared plus 9x squared minus 5x plus 6. So that first polynomial, 6x minus 2x squared, is not written in standard form. Now you could rewrite it so that this one is in standard form, but you don't have to. Again, thinking about just largest powers, right? The largest power is x squared here. So when I add these two together, I'm going to add the negative 2 and the positive 9, right? Those are my x squared terms. Then in terms of my x to the first, I've got positive 6 and negative 5. And in terms of my constants, all I have is that last positive 6. That's it. I'm going to make sure that you can see that it's positive there. So at the end of the day, negative 2 plus 9 is positive 7, x squared. 6 minus 5 is 1 times x, and then plus 6. And again, just like we had that last problem, instead of having plus 1x there, we tend to just put plus x. We tend not to put 1x. Again, nothing technically wrong with putting plus 1x, but you won't likely see it in a multiple choice kind of scenario. All right, now I'm going to turn you loose on letter D and letter E. I want you to play around with these, and again, really what you're doing is combining the coefficients using addition of the same or like terms, right? Terms that have the same exponents. So pause the video now and see if you can add these two together and these two together, and make sure to have that answer in standard form at the end. Pause the video now and take a couple minutes. All right, well, let's take a look at letter D. So in letter D, we first have x minus 5 plus x cubed, and then we have negative x cubed plus 4x squared minus 3x plus 1. All right, this one can be probably the trickiest of them all, because we have to begin by thinking about this x cubed and this minus x cubed. And literally the way it would look if we wrote it out the way we have been writing it is 1 minus 1 times x cubed. We'll get to that in a bit. Now if we look at the x squared, the only x squared that we have is in this second parentheses. There is nothing to combine it with. Then when we look at x to the first, we have 1x to the first here and negative 3 here. So that would literally kind of look like this. And then finally with our constants, we have a negative 5 here and a positive 1 here. So we have something like that. Now we're not done, but I just kind of wanted to write it all out. Now here I have 1 minus 1 times x cubed. So that's like literally 0x cubed. 4x to the second. Negative 2x to the first, and minus 4 at the end. Now, unlike these other ones where we could have left it as like negative 1x squared or positive 1x, we should never leave it like this, okay? If it's 0x cubed, this is no longer a cubic polynomial, right? That term is not there. The positive x cubed, the negative x cubed cancel each other out. And our final answer here in standard form should be 4x squared minus 2x minus 4. Okay, you've got to have it like that. All right, let's take a look at the last one, which is the longest one, right? We've got 5x to the fourth plus 7x cubed minus 2x plus negative 4x cubed minus 8x squared plus 9x minus 5. Now again, like the last problem, right? This second polynomial does not have an x to the fourth term like this first one does. So I can literally leave this and just begin with 5x to the fourth. Right now, what we've got in terms of x cubed, we've got 7 here, and we've got negative 4 here. In terms of x squared, that first one has no x squared in it. So there's nothing to combine with that negative 8x squared. Finally, we've got our x to the first, which are negative 2 in the first polynomial, positive 9 in the second. And then we've got our constant, and there's only a constant term in that second one. So if we're just kind of thinking about combining the coefficients, that's all I have at this point, right? There is no x to the fourth in this term, so we have 5x to the fourth. 7 minus 4 times x cubed minus 8x squared. There's only a negative 8x squared here. Then negative 2 plus 9 times x, right? They got the negative 2, the positive 9, and then that minus 5 is the only constant term in either one of them. So at the end of the day, we've got 5x to the fourth plus 3x to the third minus 8x squared plus 7x minus 5. Whew. And that's it, right? Simple enough. Now comes the hard part of the lesson, subtraction. So let's talk a little bit about that. Subtracting polynomials. Subtracting two polynomials is harder than adding them, especially when one or both of the polynomials contain a subtraction within it. Recall, we can change any subtraction into addition of its opposite. So before we kind of get into this, let me just remind you of this, right? Any subtraction. So for instance, if I had 5 minus 3, I could think about that as 5 plus negative 3. If I had 5 minus negative 8, I could think about that as 5 plus positive 8, right? Anytime I'm subtracting something, I can think about it as adding the opposite. And that is very helpful when combining two polynomials with subtraction. So let's take a look at exercise number 5. In this problem, we are going to perform two subtraction problems. The first should be easier than the second. Change into a sum if needed. Okay, so here's what I mean, right? We've got 7x squared plus 5x plus 8 minus 2x squared plus 3x plus 1. All right, so I can think about this as typical subtraction, or I could think about it as 7x squared plus 5x plus 8 plus negative 2x squared minus 3x minus 1. In other words, right, instead of subtracting 2x squared plus 3x plus 1, I can add negative 2x squared minus 3x minus 1. Notice how every one of those terms inside of the parentheses I have changed the sign on. Now I can combine these just like I did before, because I've got 7 plus negative 2 times x squared plus 5 plus negative 3 times x plus 8 plus negative 1. My pen does not seem to want to behave. 7 plus negative 2 is 5, so I have 5x squared. 5 plus negative 3 is positive 2, so I have positive 2x. And 8 plus negative 1 is 7. So I have 5x squared plus 2x plus 7. Now, I want to say for the record, right, of course, that would be easy enough to do by just doing, well, I've got 7x minus 2x, which is 5x squared. Sorry, 7x squared. I have 5x minus 3x, which is 2x. And I have 8 minus 1, which is 7. Nothing wrong with that. It gets harder here, though. So let's take a look at this one where I have 2x squared plus 3x plus 4 minus 5x squared minus 2x minus 2. Now this one's a bit harder because when I think about it, I have to think about 2x squared minus 5x squared. That's not so bad. But then 3x minus negative 2x, that's where people start to fall apart. Because they'll just do 3x minus 2x. And they'll just do 4 minus 2. But we're really doing 3x minus negative 2x and 4 minus negative 2. So for many people, it's a lot easier to change this problem into this problem. That stays the same. Change the subtraction into addition and add the opposite. Negative 5x squared plus 2x plus 2, right? And now there's way less of a chance we're going to mess it up. In fact, without writing out all of this, let's try it just now, right? We have 2x squared plus negative 5x squared, right? And that's going to be negative 3x squared. Plus, now I've got positive 3x plus positive 2x, which is going to be plus positive 5x. And now I have positive 4 plus positive 2, which is positive 6. Do you have to do that? No. You know, if you're comfortable with saying 3x minus negative 2x is positive 5x, awesome. I mean, like really awesome. If you're also comfortable with 4 minus negative 2 is positive 6, also really great. But a lot of students, even good math students, can very quickly look at this and go, 2x squared minus 5x squared is negative 3x squared. 3x minus negative 2 is 2x, right? Or 3x minus 2x is 1x, right? And then 4 minus 2 is 2, right? It's very easy to do that when what you really should be doing is adding instead. All right. Now, subtracting polynomials can be particularly challenging when they aren't written in standard form. So let's do one more with subtraction. Let's take a look at exercise number 6. Find each of the following differences, right? Subtraction is just called a difference. Change into a sum of opposites and arrange vertically if needed in order to combine like terms. Okay, so what I'd like you to do is play around with both of these, see if you can do both of these subtraction problems. Be careful, right? And then we'll revisit them. All right, so in the first problem, I've got 4x minus 3x squared plus 8. One of the immediate issues is that first one's not written in standard form. Not a really big deal. A lot of people can handle that without rewriting it. But I'm going to actually rewrite this first one. Let me bring this up to the top. As negative 3x squared plus 4x plus 8. Okay? Then I'm going to rewrite the second one by changing it into an addition of opposites. Right? So I'm going to change that subtraction into an addition. And I'm going to make everything the opposite inside of here. So instead of negative 6x squared plus x minus 1, I've got positive 6x squared minus x plus 1. Now we're back to it being pretty easy, right? I've got negative 3x squared plus positive 6x squared. Negative 3 plus positive 6 is positive 3. I've got positive 4x and negative 1x, which would be positive 3x. I've got positive 8 and positive 1 gives me positive 9, right? Pretty easy. Take a look at letter B. I've got 14 minus 6x plus x cubed minus 9x minus 2x squared plus 5x cubed minus 8. Whew. All right, both of these two aren't written in standard form, and we've got a subtraction. So the first thing I'm going to do is rewrite the first one. All right, in standard form, that's going to be x cubed. There's no x squareds there, so I'm just going to put minus 6x plus 14. I'm going to change that subtraction into an addition of opposites, and I'm going to also try to write it in standard form. Originally, that was positive 5x cubed. I'm now going to make it into a negative 5x cubed because I've changed it into its opposite. Negative 2x squared is now going to become a positive 2x squared. Positive 9x is now a negative 9x, and negative 8 is now a positive 8. Again, I am changing subtraction into addition of opposites. Now it's not that bad. I have positive 1x cubed, negative 5x cubed. When I combine those two coefficients, it's going to be negative 4x cubed. There are no x squareds in that first polynomial, so I'm just going to do 0 plus 2. And that's going to be 2x squared, right? Then I have negative 6x and negative 9x. That'll be negative 15x. Positive 14 and positive 8 is positive 22. Okay. Again, subtraction of polynomials is relatively easy. The problem is you really want to change it into addition of opposites. Once you've done that, then it's just an issue of adding signed numbers, right? And ever since in 7th grade, you learned how to add and subtract signed numbers, right? Ever since then, it's always been subtraction that's worse, always. And almost always, when you've had to subtract signed numbers, you've changed it into adding the opposite. So, right, when you have something like 5 minus negative 3, you almost always go, well, 5 minus negative 3 is 5 plus 3. It's 8, right? You know, you have to think about it that way. And it's very similar in a situation like this. All right. So today we reviewed quite a bit about polynomials and the fact that polynomials are very similar to whole numbers, right? And because they're similar to whole numbers, they add and subtract similar to whole numbers, i.e., when you add two polynomials together, you are simply combining the coefficients of like terms, of terms that have the same powers, right? And when you subtract, it's the same thing. You're really subtracting the coefficients of terms with like powers, but you have to be careful with that. And my advice, right, is to change the subtraction into adding opposites. That will always make your life easier. We are going to do an unbelievable amount of adding and subtracting polynomials as we go through this unit, but it's going to be one of those things where it's just a small part of a larger problem. So make sure that you really kind of understand what's going on with that. For now, I just want to thank you for joining me for another Algebra 1 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.